Okay, so this video is looking at the quotient rule for differentiation. So when we are trying to differentiate a function that can be thought of as a quotient, that is a division of two other functions. So for example, is something as simple as x plus 1 over x minus 1 can't be simplified any further. Two functions, two linear functions being divided, okay, it is not just going to be the derivative of the numerator divided by the derivative of the denominator, which would be 1 over 1 and 1. The gradient of that function is not constant at 1. So we need to think about a quotient rule for differentiating quotients of functions. So again, I'm going to differentiate by first principles. So remember, it is about taking your function at x plus h, which is what that is, subtracting that same function, dividing it by h. So rather than write it as, so obviously we could have straight away gone to f of x plus h over g of x plus h, so that's the function h, minus the original function, and then dividing all that by h. But rather than have these fractions in fractions, I'm writing that as 1 over h, and we'll worry about the 1 over h as we simplify things. Okay, so once again, so that's that first line there. Once again, and then what I've done here at the second line is to get a common denominator. So common denominator of g of x plus h times g of x is going to give us this. Okay, so now we've got this one fraction here. Okay, so once again, like the previous video, I've chosen to subtract f of x times g of x and add f of x times g of x, so it's 0, so I haven't actually changed it. But again, this is going to enable me to split this fraction in half in a way that I'm going to be able to then simplify. The other thing I'm going to do actually is I'm now going to swap out these denominators. Okay, let's just be clear about what I'm doing there. So if you have 1/3 times x plus 5 over 4, that is the same as having 1/4 times x plus 5 over 3. Okay, because it is the same as having 1/3 times 1/4 times x plus 5, which you can choose to write as 1/4 times 1/3 times x plus 5, and therefore 1/4 times x plus 5 over 3. So we can swap those denominators, so I'm actually going to do that at the same time as well. Okay, so I'm going to go with, and we'll put it back in a bit later, but it's just going to enable me to simplify a bit more easily. Okay, so we're going to have 1 over g of x plus h times g of x at the front, and then in here I'm going to split this fraction in two, and the denominator will now be h. So, no, I actually don't need that bracket around that g of x, sorry. Alright, so again, the other thing I'm going to look at, which I'll do at the same time, is I'm going to look for common factors in the first two terms and common factors in the second two terms. So g of x is common in those first two terms. So I'm going to take out g of x, and then I'm going to have f of x plus h minus f of x divided by h. Now again, you can have that g of x up there in the numerator of the fraction. It's the same thing as you just writing that out there, okay? Alright, so we're going to have g of x multiplied by f of x plus h minus f of x, and we've got it over h because I swapped the denominators around. And then we've got plus, now in the second two terms, f of x is the common factor, so I'm going to take that out, and then we get g of x minus g of x plus h over h. Okay, now what we might do is I might actually take the limit of that and the limit of that bracket separately. So let's think about limit as h approaches 0 of 1 over g of x plus h times g of x, and then we're going to have times the limit. Now actually I might also expand it out into this bracket here. So we're going to have, I'm going to break this bracket up into two separate sections. So we're going to have the limit of, as h approaches 0, of g of x times f of x plus h minus f of x over h, plus the limit as h approaches 0. Now be careful because I do have all of this needs to be multiplied by this bit out the front here. The limit of f of x times, now I'm going to do something interesting here as well. I'm going to factor out, because remember I'm really trying to get to seeing those derivatives by first principles. So I'm going to rewrite this by taking out the negative. So that's going to be g of x plus h minus g of x over h. I'll just move that green bracket. Sorry, with a bracket around the end of that. Okay, so we've factored out a negative in there. Okay, so again, let's look at taking this limit in this thing at the front here. So as h approaches 0, there's an h there, that's going to become 0. So we're going to get g of x times g of x. And so it's just going to be 1 over g of x squared. Alright, multiplied by, and then we've got all of this that we're working with in here. Now again, let's take the limit of some things separately. Let's take the limit of g of x and the limit of all of that, the limit of f of x and the limit of all of that. Okay, so we're going to have the limit as h approaches 0 of g of x multiplied by the limit as h approaches 0 of f of x plus h minus f of x over h plus the limit as h approaches 0 of f of x times, now again, we've got this negative here, so we're going to have the negative limit as h approaches 0 of g of x plus h minus g of x all over h. Okay, so once again, we've got that there is the derivative of f. And again, that there is the derivative of g by first principles. Okay, so what we have here is 1 over g of x all squared multiplied by, now the limit as h approaches 0 of g of x, there's no h in that, so that's just g of x, multiplied by, that's f dash x. And then we've got plus, now the limit as h approaches 0 of f of x, there's no h in f of x, and so it'll still remain f of x as h becomes 0. And then we've got multiplied by the negative of g dash x. Alright, so I'm going to write it as a fraction. I'm going to put that fraction back on the denominator now that we don't have any fractions in the bracket. So the numerator, the numerator is g of x times f dash x. Now it's minus f of x times g dash x all over g of x squared. And there is our quotient rule for differentiation. Again, I'm going to write it in a slightly different order so we think about it in the same way as we think about our product rule. So I'm going to say derivative of f times g, which is the first thing we do for product rule as well, but this time we subtract f times g dash x. So if you're consistent about how you write those two things, these two terms are exactly the same. It's you add for product rule and you subtract for quotient rule, okay? And in quotient rule, you're also going to have the square of g of x on the denominator of your fraction as well. Once again, this is a formula that's on the formula sheet, okay? Again, it will be given in Leibniz notation, so you'll have y equals u over v, which means that y dash or dy dx is going to be derivative of u, so du dx, times v, minus, leave u as it is, times derivative of v, all over v squared. And you'll get it written in that format on the formula sheet. Once again, there's no reason for getting it wrong, okay? Derivative of numerator times denominator minus numerator times derivative of denominator over denominator squared. You're going to have access to this formula in every assessment that you do. So you shouldn't ever be getting it wrong. If you're not sure about it, check it on the formula sheet before you go with it. But hopefully you'll have practiced it enough that you'll know it very well. But if not, it's always there. Check it if there's any level of uncertainty about what it is that you're doing. Okay, let's work our way through some examples requiring the quotient rule. The other thing I want to look at through this first example is that it is possible to avoid using the quotient rule, and it's possible to, instead of using the quotient rule, always use a combination of product and chain rule. What I want to illustrate though is actually, and I used to advocate, don't worry about quotient rule, just learn product and chain rules. However, often the expression that you end up with when you use the quotient rule is much easier to work with than the unwieldy expression you end up by the time you've done product and chain rule. The product and chain rule then requires a lot more simplification to get it into a form that you might be then able to solve or do something with, whereas the quotient rule tends to spit out something neater right from the outset. So I am now an advocate for the quotient rule, and again, you've got the formula on your formula sheet the whole time, so there's no reason for not being able to use the quotient rule. But I'm going to look at this example doing it the two different ways, okay? So we've got x minus 1 over x squared plus 3, so just a simple linear function divided by a simple quadratic function, so a quotient of two functions, and we're going to find the derivative of f using the quotient rule. So the quotient rule says that we differentiate the numerator, which would be 1, and then we leave the denominator as it is, and then we subtract, that's the first difference from the product rule, and we leave the numerator as it is, and we differentiate the denominator, and then we divide by the denominator squared. Okay, so let's just tidy up the numerator. So we're going to have x squared plus 3, that'll be minus 2x squared plus 2x over x squared plus 3 all squared. So that's going to be negative x squared, collecting like terms, plus 2x plus 3 divided by x squared plus 3 all squared. And you could factorise the numerator, but there's not going to be any common factors there given what the denominator looks like, so we can stop at that point. Okay, so there's your quotient rule. I want to have a look at how we could solve the same problem using a combination of product and chain rules. And ultimately you can make a choice about what you prefer, but yeah, over the years I've come to find and feel that the quotient rule generally, in the long run, you end up more efficiently with an expression that you can then work with, depending on what you might need to do after that. Okay, so let's find the derivative this time using the product and chain rules. So f of x is, let me just write it down again, sorry, what was it, x minus 1, x squared plus 3. So if we want to use product and chain rules, we would instead rewrite this as x minus 1 times x squared plus 3 to the negative 1. And we would use product rule and chain rule to differentiate that. So f dash x, so again, this time we're thinking about x minus 1 is our first function, and x squared plus 3 all to the negative 1 is our second function. Okay, so product rule, we do derivative of the first function, which is 1, and we leave the second function as it is. Then we add, we leave the first function as it is, and we differentiate the second function, which is going to require the chain rule. Okay, so in chain rule, we cover up our inside, we focus on the fact that we've got something to the power of negative 1, differentiating that is negative 1 times that something to the power of negative 2, and then we also need to differentiate by the inside, so differentiate by the shaded bit, which is 2x. Sorry, multiply by the derivative of the shaded bit, I should have said. Okay, let's tidy this up a little bit. So the first part of that function is now just 1 on x squared plus 3, plus, now here, we've got a negative, we've got a 2x, we've got an x minus 1, so we've got negative 2x times x minus 1 all over x squared plus 3 all squared. Okay, so then if you wanted to match it to your quotient rule, you're going to need a moment where you find a common denominator. So that's going to be x squared plus 3 over x squared plus 3 all squared, plus, let's write this as minus 2x squared plus 2x. And then we can put that together. So x squared minus 2x squared, negative x squared, plus 2x plus 3 all over x squared plus 3 all squared. There's just a bit more algebra required to get it to the same nice, neat answer by using the product and quotient rules, whereas when we use the quotient rule, we get straight away to that nice, neat answer. So I personally prefer the quotient rule. For this exercise, I would like you to try and practice using the quotient rule so that then you can make a decision about, okay, I've tried the quotient rule, but I really prefer product and chain rule. But as I said, you'll always have the formula with you on the formula sheet. There's no reason to get it wrong. You may as well use the quotient rule, is generally my feeling. Okay, so let's have a look at some examples here. Differentiate each of the following with respect to x. So we've got y equals x plus 1 over x minus 1, so a quotient of two linear functions, dy dx. We differentiate the numerator, which is 1. We leave the denominator as it is. We subtract. We leave the numerator as it is. And we differentiate the denominator. And then we have all of that over the denominator squared. Okay, so that's going to be x minus 1, and then we'll have minus x minus 1 all over x minus 1 all squared. And x minus x cancels out, negative 1 minus 1, so we're going to have minus 2 over x minus 1 all squared. Okay, part B. Alright, so this time we're going to think about this as being x plus 1 to the power of a half over x squared plus 1. So in this case, we're going to use the quotient rule because we're dividing these two things. But if we think about the numerator, when we differentiate the numerator, we're going to need the chain rule. So we can have a combination of quotient and chain rules here. Okay, so dy dx, we differentiate the numerator, and that's going to require chain rule. Half times x plus 1 to the power of negative half times by 1 for the chain rule, differentiating the numerator. And then we leave the denominator as it is, so that's x squared plus 1. And we subtract, and we leave the numerator as it is, x plus 1 to the power of a half. And we differentiate the denominator, which gives us 2x. And then we've got all of that over the denominator squared. Okay, so if we tidy that up a little bit, we've essentially got the issue we have here is we do need to do some simplification here because we've got a fraction in a fraction and we can't just leave an answer like that. This is also a fraction. That's 1 on square root of x plus 1. Okay, so let's just think about what's going on here. So focusing on the numerator, we've essentially got x squared plus 1 over 2 root x plus 1. That's that first term. And we're subtracting 2x root x plus 1, and we're dividing by x squared plus 1 all squared. Okay, so this is the issue, this fraction in a fraction problem. So if we want to get rid of that fraction, we're going to need to multiply the numerator by 2 lots of root x plus 1, and so we're going to do the same to the denominator to get rid of the fractions. Okay, so when we do this, on the numerator, that first term is just going to become x squared plus 1. And then we have minus, now it'll be 2 times 2, so that's 4x. And then we've got root x plus 1 times root x plus 1. If you've got root x plus 1 times root x plus 1, that's just root x plus 1 squared. And so that's just x plus 1. Okay, so this is going to become that. And then we've got all of that over 2 lots of x squared plus 1 squared times the square root of x plus 1. And then let's just tidy up the numerator there. So that will be x squared minus 4x squared. So that's negative 3x squared. And then we're going to have minus 4x and plus 1, expanding out and collecting the numerator, over 2 lots of x squared plus 1 squared, square root of x plus 1. Okay, so tidying up your fraction so that you don't end up with a fraction in a fraction. Okay, work today is a worksheet again, and the worksheet is found in Appendix E of your blue booklet.